Hello and welcome to the first lesson this week, 20.3 on tangents and chords. Have a go at the do now question on your screen and then replay the video or restart the video when you want to go through the answers. So question number 1, hopefully you've used the circle theorem that the angle in a semicircle is always 90 degrees. So we have a diameter as the centre is labelled as O. So it's passing through the centre, so this angle up here is 90. Angles in a triangle add up to 180. So 90 plus 34 subtracted from 180 will give you 56 degrees. Question number 2, using the same circle theorem. So the angle in a semicircle is 90 degrees. Now this is an isosceles triangle because these two sides are the same length, which means the two base angles are also equal. So this will be x. So 180 subtract 90 leaves me with 90 degrees to split between the two x values. So that will give an x value of 45 degrees. Question number 3, hopefully you've used the circle theorem that the opposite angles in a cyclic quadrilateral add up to 180. So for x, remember, so the 4 points of the quadrilateral have to touch the circumference, which they do. So 180 subtract 66 would give me 112 degrees for x, and 180 subtract 33 would give me 147 degrees for y. Question number 4, hopefully you're using the circle theorem that the angle subtended from the same points, so these are the 2 points here, so the angle subtended to the circumference is half the angle subtended at the centre. So x must be half of 122, so it's 61 degrees. Question number 5 is using the same circle theorem, so the angle at the circumference is half the angle at the centre. It looks slightly different here. It's just that these 2 points have shifted around the circumference so that they're kind of in the same segment, the same half of the circle. This is fine as long as you're using the one underneath. So half the 194 gives me that x is 97 degrees. Question number 6, we've got a few here. If we go in the order that the letters are labelled, so here we have an isosceles triangle because we've got the centre labelled and marked as O. So these are 2 radii, so these mean the 2 base angles are equal, so A must be 22 degrees. Then if we have a look for B, so now, hopefully you've realised that this is the angle in a semicircle. So this angle here must be 90. So 90 plus the 22 subtracted from the 180 will give me that B is 68 degrees. Here, going back to this triangle here, so we know that A was 22. So if we work out this angle here, then C is vertically opposite and will be the same. So 22 plus 22 will give me 44. 180 subtract that 44 will give me that this angle here is 136, which is vertically opposite to the C. Now for D, we have angles in the same segment are equal. So the same segment, remember, a segment is a piece of the circle cut off by a chord. Remember, a chord goes from one point on the circumference to the other. So D and the 22 are in the same segment. So that would mean that D is also 22 degrees. So let's have a recap of the circle theorems we have learnt so far. So number 1, which we used in the do now task, so the angle in a semicircle is always 90. So always look out for the diameter and then look out for a triangle with a point going out to the circumference. This is always 90. Circle theorem number 2, the angles at the circumference are always equal. They must be from the same arc. So here I've got points A and B. You can see that the angle up to the circumference here, going up to the circumference here, these are equal. They are in the same segment. Here, this is the angle at the centre is twice the angle the angle at the centre is twice the angle at the circumference. This is a slightly different version, but here, so here are my 2 points, and we've got an angle to the centre, an angle to the circumference. So this angle at the circumference is half the angle at the centre, or the angle at the centre is double the angle at the circumference. Number 4, we've also used in the starter that the opposite angles of a cyclic quadrilateral add up to 180 degrees. So each of the 4 corners of the quadrilateral must touch the circumference for this to happen. So in today's lesson, we are going to look at some further circle theorems, but to start with, let's have a bit more of a recap. So have a look at this question here. Which circle theorem? Can you identify which circle theorems we could use to find this angle here? If you want to pause while you have a go. So here we would use that the opposite angles of a cyclic quadrilateral add up to 180. So this would give me that this angle over here is 80 degrees, and then we could double it to get 160 by using that the angle at the centre is double the angle at the circumference. Pause the video while you have a look at this question. So this asks us to identify again which circle theorems. So this is angles in the same segment are equal. So here are the 2 points on the circumference, and one angle is created up here at the circumference, and from the same points there is another created. So these are in the same segment. We could get a ruler and we could draw a line, we could draw a chord, and these are then in the same segment. So this is 70 degrees. Again with this question. So for this one, we would use that the angle in a semicircle is 90. So this angle here would be 90 degrees. And the base angles of isosceles triangles are equal. So this is an isosceles triangle because this is a radius and so is this. And also these are the same here. So this would mean that this is 20 degrees here. And 90 take away the 20 would mean that this is 70. So this would also be 70 as it's the base angles in an isosceles triangle. Have a go at this one. So revealing for this one then. So here, if we were trying to find this angle here, we'd use angles in the same segment are equal. So looking at this triangle here, we've got an isosceles triangle. So if we do 180 subtract 116, that will give us 64 degrees, which would mean each of these here are 32, and then we can use that these are in the same segment. Have a go at this one. So for this one then, we would use that the angle between the tangent and a radius is 90 degrees. So we're going to have a look at this in a few moments. So this is the radius, this is a tangent. So tangent is a line that touches the circle in one place. So this whole angle here will be 90 degrees. So if we do 90 subtract 56, that will give us then that this angle is 34 degrees. We know that this angle is 65 as it's half of the 130. So 65 plus the 34 here, and if you do 360 subtract 130, you will get that that angle there was 230, and we know that the angles of a quadrilateral add up to 360, so this must be 31 degrees. So this is quite an in-depth question and using quite a lot of circle theorems mixed into one. So we're going to look at that last one a little bit further. So tangents and chords. So we're going to use tangents and chords to find sizes of angles. So our success criteria, our bronze objective, is to recall and use the previous circle theorems from last week. Our silver objective is to use tangents and chords to find the size of angles, and also we'll look at setting out some formal proofs for this. So as I've discussed earlier then, a tangent is a straight line that touches a circle at only one point. This is called the point of contact. So here we have a circle, and here we have the point on the circle, and the tangent is the line on the outside which touches it at that point of contact. Remember, we've talked about a chord because this determines when angles are in the same segment. So a chord is a line that touches the circumference in 2 points and joins them. So the circle theorem that I discussed in the last example is this: a tangent to a circle is perpendicular to the radius at the point of contact. So more formally, it's this one here. The angle between a tangent and a radius is 90 degrees. So you might want to highlight this on the sheet. Hopefully you've printed this sheet out from last week, or you've got it saved somewhere. So let's have a look at the proof for this. Please don't worry about this, just listen to it and follow me as I go through it. We will go through it back when we're in lessons, so please don't worry. Generally, questions in GCSE exams just want you to be able to recognise the circle theorems and find missing angles. It would only be one question towards the end of a paper, if at all, if they wanted to show you anything like this. So just have a listen as I go through. The diagram shows a circle with tangents drawn from point T to meet points A and B on the circumference. The radii, remember this is just the plural of radiuses, so the radiuses look OA and OB are perpendicular, and they always create right angles. So this always creates symmetry. So from the circle theorem we've just gone through, we can assume these are 90 degree. So in this triangle here, in OAT, OA is equal to OB because they are both radii in the circle, and they're equal. And OAT is equal to OBT, they're 90 degrees because I've just told you that from the circle theorem number 5. So an OT, hopefully you can see this is common to both OAT and OBT. So can you remember when we looked at congruency, we can say these two triangles are congruent to each other by the rule RHS because they both have a right angle in. The hypotenuse is common to both and it's the same length, and they both have a second length OA and OB that is the same. So this leads us to circle theorem 6, that tangents to a circle from an external point are equal in length. So if you see two tangents drawn from a circle and they meet at a point of contact outside the circle, all I need you to remember is that these lengths are equal. So looking on here then, all we've done is gone over this circle theorem here, that the angle between a tangent and a radius is 90. That is all I need you to remember. And also, if you see two tangents drawn and they meet at an external point, then these lengths are equal. That is all I need you to take away from the information I've just gone through. So having a look at this in the textbook calls it Circle Theorem 7, and it says the line joining an external point to the centre bisects between the two tangents. Okay, so it's just kind of creating a picture of symmetry. One last thing I want you to be looking out for in this diagram, chord AB has been bisected at point P by another radius. So if you see an isosceles triangle and then you see a radius out to, it generally bisects it. So OA is equal to OB because they are both radiuses in the circle. AP is equal to PB because we've just been told this bisects it. OP, hopefully you can see, is common to both triangles again. So OAP and OBP are both congruent to each other by the rule of SSS. They've got three sides equal. OA is equal to OB, OP is common to both, and because it bisected it, these must be equal as well. So all I want you to take away from that is this circle theorem here, that a radius always bisects a chord at 90 degrees. So if you see a chord and you see a radius, it will always bisect it, and I just need you to remember that. So let's have a look at an example together. So here, OA is the radius of the circle and AB is a tangent, and we've been given the length OA equals 5 centimetres and that this length AB equals 12 centimetres. The question asks us to show that the length of OB is 13 centimetres. So angle OAB, hopefully just using the fact that a radius meets a tangent at 90, we can see that this is 90 degrees here. So the radius is perpendicular to the tangent at the point of contact. So if OB equals x, because this is a right angled triangle, we can use Pythagoras' theorem. So 5 squared, remember the two shorter sides squared and added together equal the longer sides. So 5 squared plus 12 squared equals 169, and then take the square root would give me that OB is equal to 13 centimetres. So what I want you to do is pause the video and you could have a go at some of the questions from this exercise, or alternatively you could start working through the Hegarty tasks that have been assigned to you this week, and you can see the first couple will take you through these anyway. So you can pause the video and have a go at just a couple maybe from each question, or you can just go to the Hegarty maths videos and pop the answers into the PowerPoint. Some of them towards the end will be quite tricky. It looks like a couple of them are using trigonometry, so it might just be an idea to work through a few of the earlier ones, say some from questions 1, 2, 3 and 4, and then go straight to the Hegarty tasks. If you want a bit more challenge, have a look at some of the questions later on. Good luck!